Hello and welcome to your stats warm-up. All right, so this is just going to review some of the introductory concepts related to hypothesis testing. So for each of the following settings, define the parameter of interest and write the appropriate null and alternative hypothesis for that test that is described. So the mean time for college students to complete a certain paper and pencil maze is 30 seconds. All right. You wish to see if it is changed by vigorous exercise. All right, and notice that it just says changed. It doesn't say higher or lower. So you have a randomly selected group of 25 students from a particular college exercise vigorously for 30 minutes and then complete the maze. All right, so our parameter of interest is the mean time. All right, this is mean to complete the maze. All right. The null hypothesis is our statement of no difference. So that would be that the mean is still equal to 30 seconds. The alternative hypothesis is what we're testing against. And again, because this one just says, is it changed? We're not going to do a less than or a greater than. We're just going to say is not equal to 30. All right. We don't have a theory on whether it's going to increase it or decrease it. We just want to know, is it changed by vigorous exercise? All right. So that'd be the first one there. B, statistics can help you decide the authorship of literary works. Sonnets by an Elizabethan poet are known to contain an average of 6.9 new words. And the number of new words is approximately normally distributed. Now a new manuscript has come to light with many new sonnets, and scholars are debating whether it is the poet's work. They take a simple random sample of 5 sonnets from the new manuscript and count the number of the number of new words in each one. We expect poems by another author to contain more new words than found in the Elizabethan poet's poems. Right. So again, our parameter, we're dealing with a mean here, and it's the mean number of new words in a sonnet. Right, that's what we're investigating. And again, the null hypothesis is the statement of no difference. So that would be that the mean is still equal to 6.9. All right. The alternative, because we're testing to see if it would contain more new words, is that the mean is greater than 6.9. All right. So again, just this idea of like what we're actually looking for and then how we would write the null and the alternative. All right. 2. So consider question 1b. Scholars have determined that the number of new words is normally distributed with a mean of 6.9 and a standard deviation of 2.7. When you examine the 5 new works, you find a mean of 9.2. All right. Below is a dot plot showing the results of simulating 200 samples of size 5 from a normal distribution with a mean of 6.9 and a 2.7. All right. So this is effectively a sampling distribution. All right. We had a computer. We fed in this value and this value, and the computer randomly selected samples from a population with those values. All right. And then these are the results that it got from those 200 samples of size 5. So what we want to see is, all right, this is what we found in real life in quotes. All right. This is what the computer generated. And what we're going to say is, all right, based on what we saw in real life and based on what the computer generated, how exceptional was that result? All right, how crazy was it that we saw a 9.2? Is that something that could happen pretty frequently, or is that pretty rare? All right, so if we look at our little dot plot here, we can see these are all the times that we ended up with a value of 9.2 or higher. And in fact, it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 occurrences of 9.2 or higher. All right, I think I missed an R there. 12 occurrences of 9.2 or higher. So when we're coming up with our estimated p-value, we would basically say, okay, there were 12 times out of the 200 samples that we collected, all right, which works out to be 0.06. So we got a p-value of 6%. Now, if our alpha is 0.05, our p-value ended up greater than our alpha. So because our p-value is above our alpha, we fail to reject the null. All right. So 9.2 doesn't happen a lot, but it does happen 6% of the time, which is above our threshold of 5%. So even though, yes, we ended up with 9.2 and the population mean was 6.9, we don't have enough confidence to say that we're sure that these works were by a new author. All right. Seems like it could be possible, but the evidence doesn't support it to our level of satisfaction, right? Because we sort of established we would only, decide that it was meaningful if it happened less than 5% of the time, and technically this one happened 6% of the time. So we fail to reject the null. So we're not comfortable saying that this mean is actually above 6.9. Okay? Doesn't mean we've accepted the null, we've just failed to reject it. So let's take a look at the back. A certain cigarette brand advertises that the mean nicotine content of their cigarettes is 1.5 milligrams, but you are suspicious and plan to investigate their advertised claim by testing the following hypothesis. A mean of 1.5 versus a mean greater than 1.5 at the 5% significance level. You will do so by measuring the nicotine of 30 randomly cigarettes of this brand. Describe what a type 1 error would be in this context. All right, so a type 1 error is when you reject the null and you're wrong. All right, so this is reject the null and you're wrong. So in this context, it's you think there's more nicotine, when there's not. All right, a type 2 error is when you fail to reject and you're wrong. So again, in this setting, it would mean that there's more nicotine, but you failed to recognize it. Now, from the perspective of public health, which error, type 1 or type 2, is more serious? Explain why. So again, which one is more serious can depend on your perspective. But in this case, if we're looking at it from the public health point of view, a type 2 error is more serious because the cigarettes are more addictive and we don't realize it. Okay. Last one, number 4, a construction engineer for a city. You are responsible for ensuring the company is providing gravel for a new road, puts as much gravel in each truckload as they claim to. It has been estimated that it will take 500 truckloads of gravel to complete the road, so you plan to measure the volume of gravel in an SRS of 25 trucks to make sure the company isn't delivering less than they claim. Each truckload is supposed to have 20 cubic meters of gravel, so you will test the following hypothesis. The mean is 20 versus the mean is less than 20 at a 5% significance level. So describe what a type 1 error would be. We just said that a type 1 is when you reject the null and you're wrong. So this would be you think you're getting less gravel, but you're wrong. All right. A type 2 error is when you fail to reject and you're wrong. So that would be you are getting less gravel and you don't realize it. Now, which error, type 1 or type 2, is a more serious problem for the city? All right, just like the one above, I would say type 2. Type 2 error. You might not make any changes. But you're going to be short on gravel. Now, if you're the company, a type 1 error is probably more serious because then all of a sudden you're going to have the city yelling at you and claiming that you're shorting them of gravel, and you're either going to start providing more gravel or you're going to have to prove to them that you're not shortchanging them, and it's a much, bigger headache for you. So again, depending on your perspective here, the type 1 or the type 2 can be more serious. It's not like a default of, oh, this one is always more serious, this one is always less serious. It really kind of depends on your perspective. All right. So again, that's just kind of a recap of some of this introductory hypothesis testing stuff. We've got type 1 and type 2 errors. We've got the idea of a p-value, which is basically how rare is an occurrence. And then we have this idea of writing null and alternative hypotheses. All right. So hope this was helpful. If you have any questions, let me know. Otherwise, have a great day.